Good morning, everybody. Yesterday in class, the last thing that we mentioned was how to go from name to condensed structure or skeletal structures for alkynes. So far in chapter 11, we have studied how to name alkanes, cycloalkanes, alkenes, cycloalkenes, and alkynes. In today's class, we are going to finish chapter 11 by now talking about the last member of the hydrocarbon family, which are aromatic compounds, okay? So in section 11.8 in the textbook is where aromatic compounds are discussed. One of the common misconceptions about aromatic compounds is that people think that, oh, if it's an aromatic compound, it has an aroma. In chemical definition for aromatic compounds, it has nothing to do with aroma because aroma is one of those physical properties that can be present in any organic compound with any functional group. So understand that that is just a physical property that pertains to any compound in general. Now, when we define aromatic compounds in organic chemistry, those are going to be structures in which the parent chain is a benzene ring. So when we started talking about organic chemistry, we introduced these as arene compounds. So the functional group for aromatic compounds, we call them arenes, but we can also call them benzene because the presence of that benzene ring. Now, you guys can see here the different ways that we can illustrate a benzene ring. Understand that a benzene ring, it is written as a hexagon with alternating double bonds and single bonds. And in the first two structures that we have from left to right, you can see the two ways that we can illustrate those double bonds and single bonds that are present in those hexagon. And they need to be three and they need to be alternating. Now, instead of writing those lines, the alternating double bonds and single bonds inside of the hexagon, we can actually skip the lines and actually draw a circle. And you can see in the third illustration how we have a circle in the middle of the hexagon. That also represents benzene. What that circle is symbolizing is that alternating double bond and single bonds, instead of saying, oh, they can alternate, we are just going to say the circle represents all of the different ones. Now, you may not put circles and lines. That is redundant. We do not do that. You pick one of the two. You either do the lines inside of the hexagon or the circle inside of the hexagon. The last structure that we have here, the fourth one, is the skeletal formula for a benzene ring. As you can see, we do not have an illustration specifically of the hydrogens in the molecule. So understand that these are the four ways that we can actually illustrate benzene rings. Now, as we have done with all of the preceding hydrocarbons, now we are going to proceed to learn about aromatic compounds and how do we name them, okay? So as we have done so far, when it comes to things that are cyclic, and in this course, we learn about cyclic alkanes and then cyclic alkenes. When it comes to aromatic compounds, okay, let's go through the rules when we have one substituent or two or more substituents. In the category of one substituent, okay, when one substituent is attached to the benzene ring, all we're going to do, similar to what we did with the cyclic alkanes, we're going to name the substituent and you're going to put the name of that substituent as a prefix of the word benzene. No number needs to be placed in front of the substituent because wherever we have that substituent inside of the benzene ring is going to be carbon 1. Now, you guys need to be familiar with some common names that can be utilized for certain substituents that are present in a benzene ring. So here we have the following examples. As you can see in the first molecule, we have a chlorine on a benzene ring. That's why we put chlorobenzene. Now, when your benzene ring is attached to one methyl group, that can be called methylbenzene, as you guys see here. But that structure itself has a common name, and that is called toluene. If we have an NH2, and NH2 is an amino group, this structure is called aminobenzene. Now, the common name of having an amino group next to a benzene ring is going to be called aniline. I will never forget about that. The first year when I was a graduate student, I had a student, her name was aniline, spelled like this. And she will just write the structure of aniline. And I was like, wow, this kid is interesting. Like I saw in the list when she, again, this is back in the day, this is early 2000s. So when she drew the structure of aniline, I looked at it and I was like, aniline? She's like, my parents are chemists. That's my name. So I just draw the structure because they trained me how to draw the structure from childhood. I was like, wow, that's interesting. So she's kind of like Prince, that she drew a structure, but only in chemistry, people understand her name. Anyways, if you have an OH group attached to a benzene ring, an OH group is known as hydroxy, okay? And then when that hydroxy group is bonded to a benzene ring, again, we can call it hydroxybenzene. But overall, the common name of that is going to be phenol. Understand that these common names, we can also incorporate them into naming, as we're going to see in the next few examples, okay? Because these common names are going to become the parent chain, but it is important that you know them. As we have discussions for the material for exam 2, you guys are going to learn at least one more for exam 3, but at least an additional one by the time that we have the final. So we have 2 more common names that are coming later, but I will, stress on it once we get to that material. Let me highlight the methyl group, but we know that that is a methyl group, okay? So it's important that you guys know the common names for that. Now, what happens when I have 2 or more substituents attached to the benzene ring, but those substituents are not going to be that methyl, that amino, or that hydroxy group, okay? What we do when we have 2 or more substituents is we're going to number them to give them the lowest number, okay, within the ring system. Remember that we are going to number the ring clockwise or counterclockwise. So for example, here we have 2 chlorine molecules attached to a benzene ring. Notice that whenever we're numbering the carbon atoms inside of the ring. So in the first structure, those chlorines are next to each other. So we're going to do clockwise to give them the lowest combination of numbers. So they are on position 1 and 2. We need to put their location. Again, and as we have learned so far, if you have 2 of the same, you're going to use the prefix di. Understand that in the textbook, they capitalize the di. For those of you that have already opened chapter 11 chapter quiz, you will see how I test you on naming, which is in a drop-down menu. So you just have to make sure that you select the correct prefix from the drop-down menu. You guys are not typing the names, okay? If you haven't done it, please just, go to chapter 11 chapter quiz and you will see how we deal with naming in this class. But we can see here that we have 2 substituents on carbons 1 and 2. So that's where the 1 and 2 are representing the locations inside of the benzene. And then we have a dichloro group followed by the word benzene, because that's going to be the parent chain. In the second example, we see that the chlorines are in positions 1 and 3. we give their location, we say dichloro to name the substituents, and we end up with the word benzene. But what if our substituents include that CH3, that NH2, or that OH? Well, when that happens, okay, when you have two or more substituents, and the carbon in one of the carbon atoms is going to have one of those signature substituents that I mentioned earlier, that methyl dihydroxy or hydroxyl group, that amine or amino group, okay? The carbon that is holding the OH, the methyl, or the amino group is what becomes carbon 1, okay? Then you're going to number the other carbon atoms in the benzene ring to give the rest of the substituents the lowest number. And remember that the last word is going to be the common name for that special group that we have in our structure. So let's look at the examples. So one of the things that I want to specify, which the textbook does, as you can see in these examples, is that they always put carbon 1 on the top of the hexagon. I do not do that because that OH can be anywhere, okay? I don't want you guys to have the misconception that all organic molecules put that special substituent hydroxy, amino, or methyl right there on the top of the hexagon. That is not true. It could be anywhere. You need to look for it, and we're going to practice so you guys get familiar with it. But going over the rules, as you can see here, we have 3 substituents in the first molecule. We have an OH, we have a Cl, we have a bromine. So when it comes to naming, this becomes your parent chain, because we have specifically a benzene ring with one of those signature substituents. So the carbon that is holding the OH becomes carbon 1. And then we're going to number the ring, in this case, as you can see, counterclockwise to give the rest of the substituents the lowest number. The last word is not going to be benzene. If you select the signature common name, okay, it's going to be the common name itself. So that's why the last word is phenol, as we have done before. And in this case, we have 2 substituents that are going to be different. We have to put them in terms of alphabetical order. So 4-bromo comes first, then 2-chloro. In the next example that we have, you can see that this is your parent chain, the toluene common name. And in this case, we have a total of 3 additional substituents. We have 2 bromines and 1 chloro. Remember, the reason why dibromo is coming before chloro is because the di does not influence the alphabetical order. Okay, so whenever we are placing the substituents in alphabetical order, what I'm comparing specifically is going to be the B in bromo to the C in chloro. Okay, let's practice the naming of some aromatic compounds to just solidify these concepts. Okay, let's get started. First, here we have a benzene ring with 1 substituent. Let me know in the chat, do we need a number to identify the location of the substituent? Yes or no? I like those no's. Let me make sure that I have more no's in the chat. I just want to know that people get this. Great job. So if we have only one substituent inside, or one substituent attached to my benzene ring is what I should say, then we don't need a number, okay? So I need you guys to, again, that pattern recognition of the atoms that we have. I already told you methyls, okay? Let's put the chemical formula of a methyl in the chat. What does a methyl look like? Excellent, thank you guys, a CH3. So if a CH3 is attached to my benzene ring, that is toluene. If I have a hydroxy group, what are the two atoms that make a hydroxy group or hydroxyl group? Excellent job, an OH. That makes my benzene be called phenol. What about if I have an amino group? What are the atoms or the chemical formula that gives me an amino group? Great job, an NH2, okay? So don't be overlooking this one and say like, oh, I know the name of this. This is aniline. This is not aniline, you guys, okay? This group right here is known as a nitro group, okay? So what would be the name of this compound if this substituent is known as a nitro group? Great job, Gia. Exactly. This is nitrobenzene. Okay. Let's move on to the next example. This is a skeletal structure. Let me highlight. I'll put a 1 in the chat if you guys want me to put the carbons and hydrogens on the substituents. I'm not going to do it inside of the benzene ring. Great. So here we have a CH2. There's a CH2. There's a CH3. And this is a CH3. So those are my substituents, okay? Now, when I look at this molecule, what is the name of my substituent in the top? What is this? It's not an ethyl group. Great job. This is a propyl group. Remember that the difference between propyl and isopropyl is that isopropyl looks like, thank you, Gia, exactly, like a Y, okay? So if you count 3 carbons, but it doesn't look like a Y, your heart has to go to propyl, okay? Not isopropyl. Now, in the bottom, we already know what is the name of that substituent in the bottom. Great. This is a methyl group. Now, there is a special name that I can give my benzene ring when it has a methyl group, and that's going to be my parent chain. What is that special name that a benzene ring? Excellent job. You're getting the hang of this. I'm so happy. So the last word is going to be toluene. Toluene, because that becomes my parent chain. Now, as I mentioned to you guys, okay, since we identified that this is the parent chain, then that means that the carbon that is holding the methyl is carbon 1, okay? And thank you for putting the answer, okay, already here in the chat. But for those students that need to see this worked out, I'm just going to continue. For this molecule, okay, that propyl group is on carbon 4 in any direction. So if I go counterclockwise or if I go clockwise, the propyl group is going to end up in carbon 4. So let me just do counterclockwise, 2, 3, 4, okay? So that's why the name of this structure is going to be 4 isopropyl toluene. Okay. Let's do the first molecule on the second row. First molecule on the second row. Two substituents, but there's no common name. So if I have two substituents, what's going to be the name of my parent chain? What is the last word in this name? Thank you, Daniela. Exactly, benzene. Now, we learned before that if I have two substituents only, the one that gets position 1 is going to be the one that comes alphabetically first. So who's going to get position 1 in the numbering side? Excellent job, the bromine. So this is going to be carbon 1. And in this case, I have to go clockwise. 2, 3, 4, 5, 6. So then the name of this molecule is going to be 1-bromo, 2-ethyl, benzene. Questions so far?
Wouldn't that be 3-ethyl? Why is it 2-ethyl?
Oh, yeah, sorry. I think I said 3, but 2. Thank you for catching that. Yes. Let's go through the last one. I think you guys are solid in your naming. There is a special name that is going to become the parent chain. I want you guys to give it a try. What would be the name of that last structure? Excellent, phenol. I'm glad that you guys were able to find. So this is my phenol. And that's going to be the last word here. That's my parent chain, the phenol. What is the location and name for the substituents? Let's put them in order. Let's put them in the chat. What's the one that comes first? Great. Thank you for that answer. 3-ethyl. Then the 2-isopropyl. Because when we do the numbering, this is 1, this is 2, this is 3, 4, 5, and 6. Questions going from name to structure. No problem. So whenever you have a methyl group, a hydroxy or hydroxyl group, or you have an amino group within the benzene, that whole motif, and what I mean with motif when it comes to chemistry is like that whole signature structure becomes your parent chain. So in this case, because phenol becomes my parent chain, then the carbon that is holding it is what carbon 1 is. Then I'm going to number the other substituents going from that as carbon 1 in order to give them the lowest number. That only happens when, again, you have an OH, so that means that phenol is your parent chain. If you have a methyl, that's toluene. And then if you have an amino group, that's aniline. Understand that there's other, common names. I'm just giving you the basic 3 that are in the textbook, because we have silene, we have anisole. There's a whole bunch of lists for these, but you guys in this course, at least at the level of chapter 11, you only need to know those 3: phenol, aniline, and toluene. Great. Any questions naming aromatic compounds. Go ahead, Francisco. No problem. So if you have a benzene ring that does not have those signature substituents that make it have a common name, okay? Then you apply the rules that we already know for cyclic compounds, okay? So for example, if you have one substituent in your benzene, then it's name of substituent followed by the word benzene. As you can see in the first molecule in the second row, in the bromo 3-ethylbenzene, if you have two substituents in your benzene ring, then alphabetical order is what tells you which carbon in the benzene ring gets assigned carbon 1, and then clockwise or counterclockwise, you have to number the benzene ring to give that second substituent its location. Lastly, when it comes to if you have 3 substituents and there's no methyl, amino, or hydroxy, then you have to make sure that the numbering of your substituents is going to be the lowest number. So it's, if you don't have the signature substituents, then you apply the rules that we already know for cyclic compounds. Go ahead. So if we have another substituent on, like on that bromo, okay, then let's say if you have something on 5, it depends on the name of it, right? If you have something on 5, let's say that that substituent on 5 is a methyl group, then it does not affect how bromine gets carbon 1, or the carbon that in the benzene ring that is holding a bromine gets carbon 1. The only way that it is affected is if it will have like different alphabetization. Because let's say that you have the following. Right? We know that Br is bromo. We know that that is an ethyl group. Let's say that we have that triangle for some reason attached to the benzene ring. Technically, this substituent is called cyclopropyl, because this is a cyclopropane. And we learned earlier in this chapter that if you have an alkyl chain as a substituent, it ends in YL. So we just remove the ane in cyclopropane and put YL because it is a substituent. So then that name for this will be 1-bromo, 5-cyclopropyl, 3-ethyl, because cyclo comes, or I'm incorrect about that. We go the other way around. The numbering changes because we do 1, 2, 3, 4, 5, 6. So it's still 1-bromo, 3-cyclopropyl, 5-ethyl. So it depends. Because we also learned in this class earlier that if the numberings are going to be the same in this, if either direction, then alphabetical order is what breaks the tie. So understand that for the exam, you guys have a limited number of combos that I can give you. So if the numbering is the same in either direction, then alphabetical order breaks the tie. So for this one, we have to number it counterclockwise. Because in either direction, bromine is going to be number 1 because it comes alphabetically first. And all the substituents are in between 1, 3, and 5. Now, we just had the 4th of July happen this week, right? And hopefully you guys went to see fireworks. They're a lot of fun, but you guys heard a lot of detonations. That was a lot of booms, okay? One of the things that are commercially available, and depending on the state that you live, may be legal or illegal, because fireworks are illegal in some states or some counties. At least when I used to live in Texas, you could get fireworks in some counties, and in other counties you couldn't. Now, one of the things that make those large detonations is going to be the following compound. 2,4,6 Trinitrotoluene. Okay. You may not know, 2,4,6 Trinitrotoluene, but can anybody guess based on that name what that stands for? The shorthand of 2,4,6 Trinitrotoluene. Thank you, Daniela. That is TNT. Okay. Take a moment, draw the structure, because now based on the name, we can draw it. Take a moment, draw the structure of 2,4,6 Trinitrotoluene. So the first thing that you need to draw is your toluene. The carbon atom that is holding the methyl is carbon 1. Then we go 2, 3, 4, 5, 6. On position 2, we have an NO2. On position 4, we have another NO2. Position 6, we have another NO2. The reason why I wrote it as O2N is because I know that the carbon in the benzene ring is attached to the nitro group through the nitrogen. That's kind of just to warn you. That's why sometimes you see me write H3C for methyl, because I know that the attachment is through the carbon atom. Any other questions? Naming aromatic compounds. Yeah, you can also do the lines. That's correct. Exactly. We just remove the circle and add the lines. Both things are correct. Well, let's move on to the next concept in chapter 11, which is one of the most important things that we explore in organic chemistry. which is reactions. When it comes to organic chemistry, understand that these organic compounds are going to undergo chemical changes. And these are the first set of reactions that you guys need to know for exam 3. Okay, so in the textbook for chapter 11, there are 3 main reactions that you guys need to know. 2 of them are summarized in table 11.7. The first one is hydrogenation. So hydrogenation means that hydrogen is added to the functional group that we're interested in. Hydration, just like if you're hydrating yourself, we're adding water to the functional group that we are interested in, okay? Understand that these addition reactions are going to be particularly present in things that are unsaturated hydrocarbons, okay? So when it comes to hydrogenation, you can see that in table 11.7, they only gave you alkenes. But understand that for hydrogenation, we can have them in alkenes or alkynes, okay? What happens in an alkene or an alkyne when it undergoes hydrogenation is that we are going to break the carbon-carbon double bond in the case of the alkene, or break the carbon-carbon triple bond in the case of the alkyne, and we're just adding hydrogens to the carbon atoms that used to be either double bonded or triple bonded to the point that they become alkanes. So I always say that this reaction is kind of like that Oprah moment in organic chemistry. You get a hydrogen, and you get a hydrogen, and you get a hydrogen, or you get a hydrogen, but only the ones that were either carbon double bonded or carbon triple bonded. The goal of hydrogenation is that we're turning those alkenes or alkynes into alkanes, okay? Now, in order for this reaction to proceed, you need a catalyst. Now, it depends which catalyst you have available. In the laboratory, you can use any of those 3 catalysts. You can use platinum, you can use nickel, you can use palladium, okay? Any of those 3 catalysts, these are chemical catalysts. Remember that what they're doing is increasing the rate of the reaction, but they're not affecting the potential energy of the reactants and the products. We are just reaching the product faster by decreasing the activation energy. Remember that the utilization or the use of catalysts we already explore in chapter 7. You know, what is the purpose of them? And that's what happens in the process of hydrogenation. Hydrogenation is one of those reactions that I keep very close to my heart. This was my first fire as a chemist, because this is the reality, you guys. I was working with palladium. Now, palladium, they usually put it in charcoal. And if you're not careful, once it touches air, if you expose it to air, it actually catches on fire. The problem is that hydrogen is actually explosive. So I was doing very well with my reaction. I added my palladium slowly. For some reason, part of my palladium did not get coated in my solvent. And when it reached the tip of the, like what I was using to actually pour it into my reaction, it caught on fire next to my hydrogen balloon. I just threw sand in the hood and ran out. That was it. So I was like, interesting. We need to be very careful. This is why we study chemistry. I will never forget. It was one of those epic moments in my chemistry career. I was like, wow, I was about to explode a whole hydrogen balloon inside of a hood with flammable solvent. So nothing major happened other than the little palladium catching on fire, but at least the balloon didn't pop, because that would have been a big explosion. But I will always remember hydrogenation and how to be very careful with it, because it can be a disaster. Now, let's move on to the next addition reaction, which is hydration. When we are hydrating, okay, a particular functional group, in this course, the only thing that we are hydrating is going to be alkenes. Now, even though in this class, we don't do what is called mechanisms. In organic chemistry, mechanisms explain the flow of electrons. In Chemistry 104, we visualize reactions more into the cookie cutter chemistry, I like to say, which means that I want you guys to visualize, okay, these reagents are going to cut into these pieces and they're going to be glued onto my functional group in this following way. So when it comes to hydration reaction, even though you know water is there, what I want you guys to visualize is that this water is going to give to a portion of a molecule a hydrogen, and is going to give another portion of the molecule OH. This needs to be done under strong acidic conditions. Usually sulfuric acid is what we utilize. So if you take an alkene and you break the double bond, and then to one of those carbon atoms, you add the hydrogen, and to the other ones, you add the OH, because you're adding OH to a carbon atom, then that means that we're making an alcohol, okay? So understand that there's actual parameters of who gets the hydrogen and who gets the OH. As you can see in the first bullet point, a hydrogen atom from water forms a bond with the carbon atom in the double bond that has the most hydrogens. In organic chemistry, at times myself and other colleagues, we learn in our training that this is what we call the richer gets rich. The most hydrogen atoms that a carbon atom has, the incoming hydrogen joins those hydrogens. So if you already have H's, you will get the incoming H. The other carbon atom will get the OH. And that's basically how we do the addition reactions. Again, hydrogenation, if you're an alkene, break that double bond, you get two H's. If you're an alkyne, you break 2 out of the 3 bonds in the triple bond, and then each carbon atom in your triple bond gets 2 hydrogens. In hydration, in the double bond, you break it, the carbon atom that already have H's will get the incoming hydrogen, its neighbor will get the OH, okay? And those are the addition reactions. In chapter 11, we deal with one more reaction, which is combustion. Understand that combustion can happen to any hydrocarbon. Specifically in the textbook, they focus on the alkane. As I mentioned to you guys earlier this week, when it comes to alkanes, for example, if you were grilling during this 4th of July holiday, you use a propane tank, unless you use charcoal. But if you utilize a propane tank, what you were using is using that alkane, aka propane, you expose that gas to the air because the air has oxygen. Those two things combine, and when you spark or you put fire in it, that's why we have a delta in the reaction, that created energy in the form of a flame, and then you converted the atoms into CO2 and H2O. So every time we have the combustion of a hydrocarbon, and here we have illustrated alkanes, your products are going to be CO2, water, and energy. When it comes to combustions and hydrocarbons, I don't make you guys balance the equations because balancing combustion reactions can be a pain in the butt. So understand that I want you to understand, okay, if Dr. Luz gives me a hydrocarbon and O2, and there's energy put in the system, my answer is going to be CO2, water, and energy. I do not need to balance it. So taking into account that we went over these 3 reactions, let's now do practice problems on predicting the products of reactions. Understand that when it comes to exams, there's different ways that I test you guys on these. I can give you the reaction in words, and then you have to select the correct structure. I can also give you the reaction as you see it here, and you select the product from the structures given. I can give you the reaction like this. I can put the product in words, okay? So there's different ways in which I test you on these. Understand that for chapter 11 chapter quiz, there's no practice per se on predicting the products, but I'm going to incorporate it into the extra credit for exam 3. So you guys see the different flavors of the questions when it comes to predicting the products of a reaction. The main thing when we are predicting products of the reaction is that you need to know what reaction are we dealing with. And all you have to do, you guys, is keep track of the functional groups and the reagents that they're being exposed to, okay? So let's actually go through these 7 reactions just to solidify the concepts of reactions. Reaction number 1. I have an alkane that I am reacting with O2 and I'm heating it. What kind of reaction is that? Actually, let me just put the 3 reactions that we talked about. Let's do in letters. If A is hydrogenation, B is hydration, and C is combustion. Reaction number 1, what are we doing? A, B, C, A, B, or C? Great way to observe. So number 1 is a combustion reaction. It doesn't matter how the molecule looks like, okay? Here I gave you an alkane. Any hydrocarbon will be undergoing combustion. Every time you see a combustion, don't even think about it twice. The product of those reactions is CO2, water, and energy. Always, 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 okay? Let's move on to reaction 2. Is that hydrogenation, hydration, or combustion? We have an alkene reacting with H2 and palladium. What kind of reaction is that? Great job identifying. This is hydrogenation. For those students that are like, I don't know how people knew that it was hydrogenation. Look at the reagents. H2, palladium. Okay? So, how do I predict the product of this reaction? Let's at least draw the structure first. If you need to draw the product, I want you guys to just redraw the structure, but do not include the double bond. So I'm going to have a carbon atom right here. I'm going to have a CH3 here, a CH3 here. Instead of a single bond, a double bond, I'm going to do a single bond. This is a CH. This is a CH2. This is a CH3. Now, if I'm doing hydrogenation, what atom is each of these carbon atoms going to get? What atom? Excellent, a hydrogen. So this becomes CH and this becomes CH2 because we're making an alkane. Let's take it up a notch. Let's review some of the stuff that we have done this week. What is the name of this reactant? Just put it in the chat. What is the name of that reactant? What is the name of that reactant? The reactant is the whole molecule. Yes, there is a methyl group in it. Yes, just the ones that were double bonded are the ones that get the hydrogens. Because remember that the only function, what's happening is that the addition happens to the atoms that were double bonded. Let me highlight that. So these guys had the double bond, so these guys get the hydrogens. What is the name of the reactant? What's the name of the alkene? Yes, pentene is the last word. Good. Let's put it together. So pentene is the last word. I need a location for my double bond. I need the location and the name for the substituent. Thank you, Gia. Yes, this is 2-methyl 2-pentene. What is the name of the alkane? What is the name of the alkane? Great job. 2-methyl. We don't need the 2. 2-methyl pentane. Because think about it. What is the 2 telling you about the alkane? Nothing. So it's 2-methyl pentane. Okay. But this gives you guys a flavor into, okay, if Dr. Luz gives me the name, and then I have to select the name of the product, remember that your ene, I want you guys to see, this is not that bad. It's just that we have to make connections. This is why critical thinking is so crucial. My ene turn into my alkane. This remained the same. So for this exam, if you see these trends, again, that 2.5 hours will be enough time for you to finish the exam. But this is why I'm training you guys to, again, do this thinking, because there's going to be a variety of questions when it comes to this. So if you have a hydrogenation of an alkene, the part of the name that used to be the alkene, it turns into alkane. Okay. Let's move on to the third reaction. What kind of reaction is number 3? A, B, C? Which one? Excellent job. This is another hydrogenation. So in this hydrogenation, we're going to redraw the structure. And we're not going to include the double bond. And remember, if I draw the skeletal, I'm done. Because what's happening in hydrogenation is that this atom received the hydrogen, this atom received the hydrogen. In a skeletal, I do not have to write in those hydrogens. So that's my final answer. Let's move on to number 4. What kind of reaction is number 4? A, B, or C? Great job identifying the type of reaction. This is a hydration reaction. For those students that are still like, I don't see it, Dr. Luz, how do I know it's a hydration reaction? Hydration, we have water. That's how you know it's a hydration reaction. As I mentioned to you guys, in a hydration reaction, what you need to visualize this is that somebody's going to get a hydrogen, somebody is going to get an OH. Okay? I look at my alkene. Okay? I'm going to focus on my carbon-carbon double bond. Now, this is the trick about hydration reactions. The hydrogen is going to go to the atom that has the most hydrogens directly attached to them. Let me write that down. The hydrogen atom goes to the carbon at the carbon-carbon double bond with the most H's directly attached to it. Okay? The OH goes to the remaining carbon in the carbon-carbon double bond. Okay? So whenever we're adding, we're erasing the double bond and then placing or adding the atoms that we're adding. Okay? So when I'm predicting the product of number 4, I'm going to write the atoms. This is a CH3 attached to a CH. Then I have to single bond this to carbon. This is a CH3. This is a CH. This is a CH3. And this is a CH3. Okay? I'm still focusing here. If I label these carbons across that double bond as A or B, who gets the hydrogen? Carbon A or carbon B? Great. So this goes from CH to CH2. What does the carbon get? The OH. So in hydration reactions, somebody gets an H, somebody gets an OH. That's how we make the alcohol. In chapter 12 is when we learn to name alcohols. So that's why I'm not going to name this. I just want to illustrate who gets what. Sorry, it's hard to see the 2. Let me just do it a little bit larger. Oh, I think that made it worse. Okay, let's practice the last 3. What kind of reaction is number 5? A, B, or C? Excellent. This is a hydrogenation. Now, I mentioned to you guys that we're turning that alkyne into what functional group? When we're doing hydrogenation, what is the functional group that we're going to have? What is the name of the functional group that is the product of a hydrogenation reaction? Excellent, an alkane. So in a reaction like this, where you're given an alkyne, the main thing that you have to do is keep track of the carbon atoms. And I showed you guys yesterday, if you're given the skeletal of an alkyne, how to identify the carbon atoms in there. Let me write them in. This is carbon 1, carbon 2, 3, 4, 5, 6. That is in my longest parent chain. And out of carbon number 4, I have a methyl group. So what does that mean in terms of my product? That I'm going to have a CH3 connected to a CH2, connected to a CH2. So this is carbon 4, carbon 5, carbon 6. Out of carbon 4, we have a methyl. Let me number the carbons. This is 1, 2, 3, 4, 5, 6. So that area of carbons 1 and 2 became an alkane. So each of the carbon atoms is going to receive 2 hydrogens. So there's 4 hydrogen total added. And you know that there's 4 hydrogens because of this, 2 H2, so 2 moles of H2. Any questions so far? Yes. Alkenes get 2 hydrogens, 1 on each of the carbons in the double bond. In alkynes, they get a total of 4 hydrogens, 2 hydrogens on each of the carbon that used to be triple bonded. That's how it goes in the hydrogenation. Let's go to number 6. What kind of reaction is number 6? A, B, or C? Excellent, also A. Now, let's just pay attention to this molecule, okay? Because what is the functional group placed here? What is the functional group that I have in my reactant? Exactly, that is a benzene ring. So there's a question in the chat. So for the question in the chat that you still go to an alkane, yes, but let's just rationalize of why is it that I need 1 mole of H2 for an alkene and 2 moles of H2 for an alkyne. So if you think about it, once you have deleted the double bond, right? And here there's only 2 hydrogens. You have a carbon atom and a carbon atom. Here's carbon and carbon. This has a hydrogen already. So what happens is that these 2 hydrogens, again, 1 goes here and 1 goes there. And now each of the carbon atoms have a full octet. They all have 8 electrons around them. So for an alkene to turn into an alkane, it only needs 2 hydrogens on each of the carbons that used to be double bonded. If we look at the case of the alkyne, and then I write in similarly the number of carbons and hydrogens. This has a hydrogen. This is carbon by itself. So at first, this is carbon by itself, and this carbon had a hydrogen. So see how there's 4 hydrogens? Is because this one got 2, and now it has a full octet. This got 2, and now it has a full octet. So that's why alkynes need the 2 moles of H2, because each carbon atom that used to be triple bonded gets 2 hydrogens. And then in the alkene, only 1 mole of H2, because each carbon atom that used to be double bonded only needs 1 hydrogen each in order to achieve the octet. Does that clarify your question? For this class, you don't. You don't see only 1 H2. You see 2 H2s for the alkynes. Going back to problem 6. Great. You guys identified in the chat correctly. This is a benzene ring, right? Specifically, this is toluene. Now, I mentioned to you guys that alkenes need H2 or for turn into alkanes. Alkynes need 2 H2s to turn into an alkane. It doesn't matter if I put 3 H2s with the catalyst, okay? One of the things that I want you guys to know is that benzene rings or any aromatic compounds, when it comes to their chemistry, they do not behave like alkenes. So if you try to hydrogenate a benzene ring, you have to do it into a very pressurized system. And I'm not putting the units of pressure here. I'm just saying, oh, if you put benzene and you hydrogenate it, this, you guys, will have no reaction. In other words, no product. Simply by the fact that benzene / aromatic compounds do not react like alkenes. They have their own set of reactions. They are actually called substitution reactions. So do not assume that benzenes are going to react like any of the reactions that we do with alkenes. They don't. And in this class, we actually don't go into the substitution reactions that benzenes undergo, but understand that when we have benzene, they do not react like alkenes. So if you put an alkene, okay, under hydrogenation conditions, that will produce a product, but a benzene ring do not. Also, if you take a benzene ring and you put it under hydrogenation, hydration conditions, also is a no-go. But I just wanted to illustrate that, okay? Let's go through the last one. Number 7, what kind of reaction is that? A, B, or C? Great. Letter B. That's a hydration reaction. How do I know it's a hydration reaction? I have water and acid. It doesn't matter if I start with the acid and then the water, I put first the water and the acid. As long as you see H plus H2O or H2O H plus, that means hydration. So for this molecule, let me write in the carbons just to assist the students that still need to see the atoms in it. So this area of the molecule is what's reacting, okay? So when I redraw the molecule, I redraw it without including the carbon-carbon double bond. There's a methyl here, there's a methyl here. And this is where my double bond was. There was a carbon atom right here. There was a carbon atom right here with a hydrogen. If I label these guys A and B, who gets the incoming hydrogen? Carbon A or carbon B? Great. So this turns into a CH2. What does carbon A get in a hydration reaction? The OH. Questions about how to predict the products of hydrogenations, hydrations, or combustions? Then let's go on break.